Welcome to the new lecture on principal stress and Castigliano's theory. Till now in the course we have been studying about forces, units, then we moved into stress strain relationship. From there we moved towards material, homogeneous, heterogeneous, and under heterogeneous we saw anisotropic material. In this lecture we will predominantly focus on principal stress. Why is this important? When we are trying to manufacture a part to meet out to the requirements, we have to do some stress analysis. In order to make our stress analysis more closer towards the real application, we have to have some brief knowledge about principal stresses and this theory. In this lecture, the content we will see principal stress, then stress and its type, what is plane stress condition, then introduction to Mohr's circle diagram, then Castigliano theory, one or two numerical problems, and finally we will have a recap. So, principal stress. Principal stress henceforth I will call it as PS, refers to the maximum and minimum normal stresses that occur at a particular point within a material. Why is this important? Because at a particular point the stress levels can be very high. At particular point the thermal stresses can be high because of the friction whatever happens. So, it is always a good idea to find out the principal stress. Principal stress refers to maximum and minimum normal stress. I hope you will remember what is normal stress that occurs at a particular point within a given material. These stresses act on mutually perpendicular plane where the shear stress is 0. This is very important. So, these stresses act on mutually perpendicular. So, if you try to take this as x, y and z, they are mutually perpendicular. So, that is what you see here, sigma 1 this is positive, negative, this is positive, negative, this is positive, you can have negative, right. Sigma 1, sigma 2, sigma 3. The principal stresses are critical in the analysis of stress because they help in understanding the extreme values of stress that a material experiences, which is vital for predicting failure. In the entire plane, there can be few points where there is maximum stress. Because of this maximum stress, the failure can start. The rest of the plane will be as normal as possible, leaving that 3 points. Okay. That is what is very important. Principal stresses are critical in analysis because it tries to understand the stresses that material experience so that it can try to predict the failure. Mathematically, principal stresses can be found out by a tool called Mohr's circle, or it can be done through stress transformation equation. That means to say sigma 11 to transform to sigma 22 or sigma 11 to shear, whatever it is. We will see some problem in that direction. We will try to solve some problems in the tutorial. So, mathematically, principal stress can be found using stress transformation equation or Mohr's circle. Mohr's circle is a graphical representation of the states of stress at a point and helps in determining the principal stresses and their orientation. Mohr's circle is easy, it is a graphical representation. And in the graphical representation, we try to represent the state of stress at a point. Okay. So, when we stress at a point, which helps in determining the principal stress and their orientation. Okay. Why is principal stress important in machine design or part design, whatever it is? Let it be a camera stand, let it be a chair, let it be a laptop, let it be a engine shaft. For everything, we do a design, and if you do it for a machine, it is called as machine design, right. So, why is it very important? It helps us to predict failure, assesses material limits, it identifies the principal stresses, which helps in determining if a material will reach its failure point under applied loads. When we talk about safety and reliability, we sit in a chair with the confidence that the chair will withstand our load. We sit in a car hoping that the car has all safety measures, and whenever I drive at 100 kilometers per hour, all the mechanical parts has a reliability that it will not fail. Think of it, the flight tries to fly at a speed of 400 kilometers per hour or 800 kilometers per hour. A typical car in a express highway road travels at a speed of 100 kilometers per hour. How are we able to reach this speed? Some cars even go 160 kilometers per hour. How are they able to drive this? The driver has a confidence that the system will not fail. That is nothing but reliability. You have to inbuild safety and reliability into your system, right. So, safety and reliability, by comparing principal stresses to material strength properties, engineers ensure that the design is safe and reliable. All mechanical components will be designed for safety and reliability. A process will be developed for its repeatability. Please try to distinguish the difference. A chair, a spoon, a keyboard, a TV, everything will be designed for its reliability and safety, here in which our prime focus is only on mechanical loading. So, why is it important in machine design or in engineering field? Our focus here is more towards mechanical. In engineering field is because it helps in predicting failure. Can the same theory be used for electromagnetism? Yes. When we try to build a circuit or a small device which is used in aerospace industry, automobile industry or biomedical, there is a EMI test which is done, EMI and EMC test which is done. So, wherein which the safety and reliability of the circuit will be predicted, right. And it more than predicting the failure, it helps today in optimizing the design. So, here the stress concentration points are figured out, and accordingly the part geometry are nowadays made complex. For example, earlier we used to have flat plates for resting objects. Today, we have started making grooves in the flat plate through which the stress concentration points are eliminated and through which the lubricants can easily flow. By doing so, the friction is reduced. So, once the friction is reduced, the longevity of the component is enhanced. So, optimizing design, it tries to find out the stress concentration and helps in changing the design. So, stress concentration, principal stress analysis highlights the areas where high stress concentration points are there. Next, design modification. Engineers can modify design to minimize stresses, resulting in a more efficient and a durable product. So, according to the prediction of failure and optimization, the material choice is made. Appropriate materials are chosen for a given application. Appropriate materials, understanding the principal stresses aids in selecting the right material for specific application. The next one is strength and properties. Engineers choose materials with suitable strength and properties to handle the expected load. So, as I told you in the beginning, there are three principal stresses: sigma 1, sigma 2 and sigma 3. All the three are principal stresses acting mutually perpendicular to each other. Moment there is a shear load, you have to resolve the sigma 1, sigma 2, sigma 3 accordingly to get the shear or the torsional load. Stress and its type. So, we will try to write down the stress as a small recap. It is nothing but sigma is force per unit area. There are several different types of stresses. Predominantly, these are the 5 different types of stresses which act on any given material. It can be one type or a combination of one, or I can say 2 or more. More types can happen. Typically, in real time application, no single load acts. Typically, in a real time application, there will always be a combination. It can be compression stress and torsion. It can be tensile and shear. It can be compression and bending, right. So, all the 5 are important. We will always try to keep these 5 different types of forces to solve any problem. So, compression sometimes once you compress, it leads to bending also, or it can be exclusive bending. For example, if you sit on a plank, you sit, then it is bending. If you compress a spring, compression happens leading to bending. Tensile, of course, yes. Then shear, when we are trying to apply a torsional load, we try to push it and then try to do a torsional load. So, there can be a shear component, there can be a torsional component. Shearing is almost slipping of cards, which we saw, and application for shearing is all the metal cutting operations undergo shearing force. Torsion is drilling. When you do a drilling operation, when you do a screw turning operation to fasten, it is torsion. So, you will have 5 different types of stresses which act. So, stresses means 5 different types of loads. Types of stresses: normal stress. Okay. So, if you go back, I have defined here the normal stress. I have defined here. So, what is a normal stress? Normal stress is a stress that develops when a force is applied perpendicular to the surface of the object. You should also understand, many a times the object might have a profile like this. When you apply tension here, it is not perpendicular to the surface of the object. Or we can try to take a ball. Okay. You try to take a load like this. So, in real time it can happen. So, that is why we are defining normal stress very clearly. Normal stress is the stress that develops when a force is applied perpendicular to the surface of the object. It can be longitudinal, compressive or tensile, depending on whether the force is pushing or pulling on the object. It can also be volumetric, where the force acting in all the three dimensions of the material. For example, hydrostatic pressure. You are trying to take an object inside water. Compressive stress. So, this is one type. Compressive stress, it squeezes the material together like pushing down on a sponge. The third one is tensile stress. It is the stress that tends to pull the material apart. We saw an example of rubber band. Volumetric stress, it takes place when the deformation force affects an object in all the three directions, changing its volume, is volumetric stress. Shear stress tau, it acts when the object is subjected to opposing forces that act parallel to each other, but in opposite direction. I said you have liquid which is flowing, right? Liquid which is flowing, this is a plate, there is a liquid which flows through that. So, now if the top surface is moving and bottom surface is stationary, right. So, then it is one phase moving in the opposite direction of the other. So, it acts when the object is subjected to opposing force that acts parallel to each other, but in opposite direction. Torsional stress, it occurs when a material is subjected to twisting or rotational force. The individual layers of the material deforms and get twisted relative to one another. There can be a bending stress, this is bending, right. So, when you are trying to take a rod and bend it to make into a hook, that is bending, right. When I take this pen and I try to bend it. So, it is the stress resulting from application of bending moment to a material, causing it to deform. When I bend it, you see it is interesting. When I bend it, I put a load here. So, this is compression, this is tensile. So, there is a combination of tensile stress and compressive stress, right. It results in a combination of tensile and compression through its cross section. Hence, developing a stress gradient, because here on the top there is a tensile, bottom there is compression, somewhere the tensile should come and get converted into compression. So, for example, if you have an object like this, when you try to bend them, you have tensile and then you have compression. So, you have the axis. Somewhere from here to here, there is a transition happening. That is what is stress represented as or told as stress gradient. The stress changes across. So, you take a cross section, here it is tensile, here it is compression, from here to here there is a change. For example, if I say this is tensile, so this is tensile, I say tensile stress along the direction, this is compression. So, here this is a gradient. So, a stress gradient that causes bending to the material. The other one is fatigue stress. All these things what we saw are all just based on loads: normal stress, compressive stress, tensile, volumetric, shear, torsion, bending. All these things are force which is related. What is fatigue stress? Fatigue stress is nothing but a cyclic loading. The cyclic loading, like for example, I try to bend, relax, bend, relax, bend, relax. So, that is cyclic loading. I drive a cycle, right? I drive a cycle wherein which the pedal is resting on an axle, and that axle from top to bottom I move, it undergoes a cyclic load, right? A switch on off is a cyclic load. A button which you press in your smartphone, on off is a cyclic load. Okay. Opening and closing of door, cyclic load. The damper which is kept on the top of a door, cyclic load. right? Opening and closing of a door when you go to the airport, cyclic load, right? The sensor undergoes a cyclic load. In an engine, when there is a engine, there are cylinders. In each of the cylinders, there is a piston which moves up and down, right? This piston which moves up and down are connected with a crankshaft. So, that is again the crankshaft undergoes a cyclic load. Fatigue stress, it is a phenomena that occurs in materials subjected to cyclic stress and strain. This leads to progressive plastic deformation and can eventually result in cracks or complete fracture after a sufficient number of fluctuations. I keep on doing on and off and on and off like this. After some point of time, you will see that this material gives off. So, it can give, when you go back to your stress strain graph, you can see ultimate strength and then slowly it goes towards, it goes down. So, you have stress, you have strain, you can see here it goes like this, right, ultimate, and after ultimate slowly it falls down, the yield strength falls down towards a fracture. This is UTS, right. So, that is what we are saying. This leads to a progressive plastic deformation and eventually results in a crack or a complete failure. So, ultimate, when it is crossed, then the crack keeps growing and then a fracture happens. In many engineering applications, including aerospace, automotive and structural components. What is plane stress? Plane stress refers to a specific stress condition within a material where the stress acting perpendicular to a particular plane is 0. For example, you take a object, okay. Here it is called as plane strain, no in the z direction. This is the x stress, this is the y stress, and when there is a shear action x and y, there is a what happens here is called as a shear stress. So, this also happens here, right. So, this is y, this is x, okay. X stress, y stress, and which happens perpendicular to this two is xy shear, and no strain thickness is fixed along the z direction. This is the z direction, right. So, if you rotate it and keep, z direction is on the top. So, in it, one of the dimension, usually z axis of the object, is kept negligible. The z whatever is there, it is kept negligible. For example, I have here an object. This object I completely reduce it in the z direction. In the z direction, okay, let us take it like this. I have x and y, whatever it is, and then I have a z direction. Now, what I assume is, whatever I do in the front plane, I will assume that everything happens in the subsequent planes. So, I assume that no z strain thickness is fixed, right. So, it is one of the dimension of the object is kept negligible compared to other two dimensions. So, here what are the two dimensions? X and y. The stress components are going to be sigma xx, sigma yy. So, when I have an object and when I am trying to pull the object, so when I am trying to pull, there will be shear also coming into existence, right. So, tau xy. Under plane stress, the stress state is characterized by three main stress components: sigma x, sigma y and tau xy. Sigma x is normal stress acting in the x direction. Sigma y is the normal stress acting in the y direction. So, x direction is parallel to the plane of the plate. Y direction is parallel to the plane of the plate. Tau xy is the shear stress acting in a plane of the plate. So, plate and shell, at both places we use the plane stress condition. Plane stress is a common assumption for analyzing thin structures like plates and shells. Plate, this is a plate. Plate means sheet metal, floor, bridges are taken as plate. Shell means it is pressure vessel, pipelines, aircraft fuselage are taken as shell. Thin plate with a center hole, cylindrical plate under edge loading. Okay. So, plane stress is a common assumption for analyzing thin structures like plates and shells. As I told you earlier, Mohr's circle is a graphical representation. It is very easy to represent it in a graphical form. So, now let us understand Mohr's circle. Mohr's circle is a cornerstone in the analysis of plane stress problems. So, the stresses which we already saw in the previous slide, square, right? It is a cube. From a cube we have said it has made into a square. Square you have x direction, y direction, sigma along the x direction are sigma x, along the y direction are sigma y, and then perpendicular, or I would say shear comes as tau x y and tau y x. Please note down the notation, right. So, otherwise what will happen if you try to write it in a inverse. Here if you write it tau x y and tau y x, instead of y x you write x y, right, then it is not the correct convention. Mohr's circle is a cornerstone in the analysis of plane stress problems. It is a 2D representation, graphical representation. It is a 2D representation of transforming equations from plane stress problems. Mohr's circle is a 2D representation of transformation equations for plane stress problems. It is a powerful graphical tool that allows you to visualize the relationship between normal stress sigma and shear stress acting on a point within a material under plane stress condition. How does it work? The first thing is axis. Mohr's circle is plotted with normal stress sigma on the horizontal axis and shear stress tau on the vertical axis, right. Horizontal axis, this is horizontal axis, I represent sigma, and this is vertical axis, I represent tau. Mohr's circle is plotted with normal stress on the horizontal axis and shear stress tau on the vertical axis. Plotting the in-plane stresses. The known in-plane stresses sigma x, sigma y are plotted on the horizontal axis. This is the horizontal axis. The shear stress tau xy is not directly plotted on the circle itself. Center and radius. Moment you represent, you have to represent, I said Mohr's circle, so there has to be a circle, right. So, a circle should have a center and radius. The center of the circle lies exactly halfway between sigma x and sigma y on the horizontal axis. The radius of the circle represents the magnitude of the maximum shear stress within the material. So, you should understand Mohr circle will have axis, then it will have axis will have stress, it will have vertical axis tau. Then since I said circle, circle will have a center point and a radius. So, now we are trying to understand where will the center point be and what will be the radius. The radius of the circle represents the magnitude of the maximum shear stress tau max within the given material. To draw a Mohr's circle for a typical 2D element, we can use the following procedure to determine the principal stress. So, define the shear stress coordinate system. Define the coordinate system for the normal and the shear stress. So, this is minus sigma x and this is tau. Tensile normal stress components are plotted on the horizontal axis and are considered positive. Compressive normal stress components are also plotted on the horizontal axis and are assumed to be in the negative direction. So, positive, negative. For the construction of a Mohr circle, shear stress are plotted above the normal stress axis when the pair of shearing stresses acting on opposite and parallel faces of an element forms a clockwise couple. So, you will have tau kept on the top as well as tau here and here. So, this is clockwise, this is counterclockwise. Shear stress are plotted below the normal axis when the shear stress form a counterclockwise couple. So, this is clockwise couple, this is counterclockwise couple. Plot the shear stress value. For plotting the shear stress value given in the problem statement, or plot generic points on the sigma x axis and sigma y axis are shown here, sigma x and sigma y, right. Plot the magnitude of the couple. So, you can see sigma x and tau xy, sigma y and tau xy. Plot the magnitude of the couple given in the problem statement with a clockwise couple being plotted above the x axis and a counterclockwise being plotted below the x axis. If no values are provided for the moment, plot generic points above and below the x axis, okay, sigma axis for tau xy as shown in the figure. Now, to obtain the center of the Mohr circle, what we do is we try to connect this point and this point passing through the x axis. The center of the Mohr circle is obtained graphically by plotting the 2 points representing the 2 known states of stress and drawing a straight line between the 2 points, drawing a straight line between the 2 points. So, here the intersecting point, the intersection of this straight line and the axis is the location of the center of circle. So, from here it here passes through the axis, that becomes the center of circle. Now, what we do is we draw a circle keeping this point as center. Draw the Mohr circle assuming the connecting lines are the diameter of the circle. Using the intersection of the diagonal straight lines and the sigma axis as the center of the circle. The stress analysis with the Mohr circle. The stress analysis on the Mohr circle, how do you find out? It tries to tell to get the normal and the shear stress values at any plane theta. Take angle 2 theta in the Mohr circle starting with the diagonal of the circle and locate a peripheral point as shown. So, what we are saying is to get the normal and the shear stress values at any plane theta. This is there at any plane theta, take 2 theta. So, at any plane theta take 2, this is 2 theta, right, this is 2 theta. Take angle 2 theta in the Mohr circle starting from the diagonal of the circle and locate a peripheral point as shown. So, now the shear stress value will be on the y-axis and normal stress will be in the x-axis. Clear? This is your y-axis, this is your x-axis. Castigliano's theorem. What is Castigliano's theorem? This theorem states that it focuses on relationship between the internal strain energy U stored in a deformed structure and the resulting deflection del at a specific point. So, it talks about two things. One is internal strain energy U stored in a deformed structure. So, when you are trying to deform, apply load, you try to deform. The relationship between the internal strain energy U stored in a deformed bend structure and a resulting deflection del at a specific point. If the strain energy of an elastic structure can be expressed as a function of generalized displacement Qi, then the partial derivative of strain energy with respect to a generalized displacement gives the generalized force, which is nothing but Q is equal to dou U by dou Q. Okay. If the strain energy of an elastic structure can be expressed as a function of generalized displacement, when you are elastically doing it in a generalized displacement of Qi, then the partial derivative of the strain energy U, okay, with respect to the generalized displacement gives the generalized force Qi. Imagine a point on a loaded structure, right? Imagine a point on a loaded structure. If you slightly nudge the point, the change in the structure's internal strain energy is equal to the force required to cause the actual displacement at the point, both acting in the same direction. If you see very closely, if you slightly nudge that point, right, the change in the structure's internal strain energy is equal to the force required to cause the actual displacement at the point, both acting in the same direction. Why is this theorem very important? It has advantages. Alternative to direct analysis, this theorem provides an alternative method for calculating deflections, especially when direct solutions might be complex. Virtual work approach can be seen. It leverages the concept of virtual work, allowing the engineers to analyze deflections without introducing actual displacement in the structure. It is used in beam analysis, truss analysis and in frame analysis. Beam analysis, determining deflection in beams under different loading conditions. You have pillar, you will have a beam. This is a beam, right? So, which is used in bridges or it is used in construction. Determining deflection in beam under different loading conditions, we can use this theorem. Then truss analysis, truss, calculating displacement in truss having complex loading. Then frame analysis, like a wooden frame, aluminum frame for window, analyzing deflection in frame subjected to bending and axial load, right. At all these places we use this theorem. So, this theorem basically goes around this equation. In this equation, you will have energy which is stored and you will have Qi, which is nothing but displacement. Castigliano's second theorem, this theorem flips the script, focusing on the relationship between the applied force and the resulting deflection del. If the strain energy of a linearly elastic structure can be expressed as a function of a generalized force Qi, then the partial derivative of the strain energy with respect to generalized force gives the generalized displacement Qi in the direction Qi. The first partial derivative of the total internal energy U with respect to force F applied to a point is equal to the deflection del at a point of application of the force in the direction of line of action. So, the second law finds its application while less commonly used compared to the first theorem. The second theorem can help in the specific scenario like compatibility check used to verify the compatibility of displacement in structure when deflections are predetermined due to other constraints. Okay. Compatible of displacement in structures when deflections are predetermined due to other constraints. Suppose you have a rod which, or let us take a shock absorber. The shock absorber spring is there, it is placed and then it is kept inside a cylinder. So, the deflections are predetermined due to other constraints. Residual force calculation in such cases, in some cases, the second theorem can be used in calculating the residual forces arise from temperature change and other effect that induce small deflections. Both the theorems have its own limitations. It takes in only linearity and the strain energy complexity. Linearity, they are primarily applicable to linear elastic material and structures with small deflection, right? Large deflection it cannot, like a cantilever swinging it cannot. Strain energy complexity, calculating the strain energy can sometimes be complex for intricate structures. The strain energy theorem, the strain energy, the fuel of deflection analysis. Strain energy is a fundamental concept in structural mechanics. Strain energy, it represents the internal energy stored within a deformed elastic material due to applied load. So, now you will be very well versed with elastic material, deflection, applied load, everything. Imagine bending a beam, the strain energy captures the invisible work done. There is a work done, right? Invisible work done on the material to cause that bending. So, Castigliano's theorem and the strain energy connection. What is the connection between these two, what we studied? Strain energy is U. This represents the total internal energy stored in the deformed structure. Deflection is Q. This refers to the displacement of specific point in the structure due to the applied load. Partial derivative. We take the partial derivative of the strain energy U with respect to the deflection Q at a specific point. This essentially means we calculate how much strain energy changes if we nudge the structure slightly at the point. Nudge is press. Applied force Q. The applied force in the theorem states that this partial derivative is equal to the applied force Q acting in the same direction at a point. In other words, the change in strain energy due to the hypothetical nudge is equal to the force that would be required to cause that actual displacement. Okay. In other words, the change in strain energy due to the hypothetical nudge is equal to the force that would require to cause the actual displacement. Why is it important? By understanding how strain energy changes with deflection, engineers can use Castigliano theorem to calculate deflection, optimize design. This can indirectly determine the deflection of a structure at a point by analyzing the change in the strain energy due to hypothetical virtual displacement. It also can use in optimized design. Knowing how strain energy relates to deflection allows the engineer to design structures that can handle load without excessive bending or deflection. Let us try to solve a numerical problem. Consider case of a plane stress shown below. Find the maximum shear stress and the plane on which it acts. So, maximum shear stress is defined as tau max equal to sigma 1 minus sigma 2 by 2, which is 50 minus 50 by 2 equal to 0. And shear stress will be nothing but tau naught, which is sigma x minus sigma y by 2 into sin 2 theta plus tau into cos 2 theta. Since sigma 1 and sigma 2 is equal to 0, tau max is equal to 0 in all directions. Okay. So, plane strain condition show the maximum shear stress. So, we will try to find out the shear stress through this formula acting on it. So, the shear stress is going to be defined like this. Let us try to solve one more problem. For the plane stress shown, find A, principal plane, principal stress, and C will be maximum shear stress and corresponding normal stress, where sigma x equal to 50 MPa, sigma y equal to minus 10 MPa, and tau xy is equal to plus 40 MPa. So, to find the principal stress, we try to do tan 2 phi p. Tan 2 phi p is equal to 2 tau xy by sigma x minus sigma y, which is nothing but 2 times 40, which is 50 minus of minus 10, which is 1.33, right. 2p, since 2p is equal to 53.1 and 233.1 degree, or p theta is 26.6 or 166.6, right. Next, this is A. So, now when it is applied, it rotates, right. So, now next is B. Okay. So, now what happens to this diagram, we will see. So, this is x, and now you will have something like this, and your sigma max, this is your theta p, which is 26.6, right. So, principal stress is equal to sigma x plus sigma y by 2 plus or minus sigma x minus sigma y whole square by 2 plus tau xy whole square, which is, when you try to substitute all, you will try to get sigma max is 20 plus or minus root 30 the whole square plus 40 the whole square, which is nothing but sigma max is going to be 70 MPa and sigma min. So, this is max and min. A min is going to be minus 30 MPa. So, when we are trying to find out the shear, maximum shear, which is tau max equal to root of sigma x minus sigma y divided by 2 the whole square plus tau xy the whole square, which is nothing but 30 square plus 40 square, which is nothing but 50 MPa. So, the angle S is equal to theta p minus 45, that is equal to minus 18.4 degrees comma 71.6 degrees. So, again now you will see the figure would have rotated like this. So, which is minus 18.4. So, the corresponding normal stresses will be nothing but sigma x equal to sigma y equal to sigma 1 equal to sigma average, which is nothing but sigma x plus sigma y divided by 2, which is 50 minus 10 by 2, which is 20 MPa, which is 1 prime average. Okay, so what we went through in this lecture is going to be, we have gone through principal stress. Principal stress, it's important in mechanical engineering. Define stress and differentiate between normal and shear. What is a plane stress condition? Why is it or where is it commonly found? What is Mohr circle? What is its purpose in stress analysis? How are principal stress identified using Mohr circle? What is Castigliano theorem and what is its primary application? How is strain energy related to the theorem? List some practical applications to this theorem in engineering. Now, what I would request you is, I would request you try to take any bridge structure, right, railway bridge, where a train crosses, right, bridge. So, you will always see a structure like this, right, and what I want is, I want you to try to find out how many members are there, what are the stresses it undergoes, and if I try to take an element here or here, try to draw the plane stress condition and assume some value, try to draw a Mohr circle, right. And next, try to take a bridge which is supported by cables. Again, try to do this analysis. Try to see what are the difference in the values and how complex it is to solve. These are the references which we have used in making this lecture. Thank you very much.